In the previous video, we quickly introduced plu-ts and we saw how it plans to handle the off-chain side of Cardano-related software. In this video, we'll see how plu-ts aims to implement functionalities to write code that will run on-chain in a language different than Haskell, in our case, Typescript. So in order to have a look at the on-chain side, I do have prepared some notes that you can find in the doc folder yplu-ts on-chain. And here I do explain that the main reason for this part of the library is that at the moment of recording this video, the only language that allows the creation of smart contracts is Haskell, whether is by using the Plutus TX library or the Plutarch library. At the end of the day, is always Haskell, and this is not ideal for the creation of smart contracts client side. You may also know that Haskell is not the language that is being run by the Cardano nodes when validating a transaction that contains some smart contract. In fact, the code that the Cardano nodes do run is written in an untyped version of the Plutus core language, and so the high-level idea to implement smart contract functionalities in languages different than Haskell is to focus only on what will go on chain. And in order to understand how this can be done, I do have also prepared a proof of concept folder in which we do have some TypeScript files to give an idea of what will be implemented, even if those are just proof of concept files, and please take them as they are. And the important ideas are instead in the notes folder, and we'll start having a look at the Plutus core specification paper walkthrough. Now, this is a walkthrough, so it might turn useful to open the Plutus core specification from IOG and have it on the side of our walkthrough. Now, the important part of this specification are highlighted here and are the section 2, in which we define the syntax of the typed Plutus core, the section 7, in which the untyped Plutus core is explained, and then the Appendix D, which explains how flat serialization works for an abstract syntax tree of untyped Plutus core programs. So in section 1, we do have a general abstract of the Plutus core, so we can just keep to the section 2, in which it is explained the syntax used in the paper and also in Plutus core programs. And here are introduced some keywords that are present and some punctuation that will be used. And it is also explained how this notation is just a shorthand for partial function application, or actually partial term application in a Plutus core program. And then there is the actual specification for typed Plutus core. Now, this might be interesting to read, but please note that the typed Plutus core will not be implemented, since type checking will be done by Typescript and built-in features of JavaScript to ensure type safety, which is the main purpose of typed Plutus core, since of course the typed version of Plutus core does not go on-chain. In fact, section 3 is all about type correctness, which is the main goal of typed Plutus core. And here we do find many abstract formulas that do explain when a type can be considered as correct. And in section 4, we do see a formalization of execution of a type Plutus core program. And here it is basically formalized what is called beta reduction in lambda calculus. If you are not familiar with lambda calculus, you can just think at beta reduction as a function application where the function do have a single argument. Section 5 is actually interesting, even if it does not really introduce anything new. This is the formalization of the built-in types, function, and values, and this section is needed since, if you remember, in section 2, we saw that there are some built-in keywords, but we did not explain what these keywords are meant to be doing. And in order to be totally clear, this section is useful for this reason. Before this section, if then else could have done anything really, since nothing was specified. With this section, it is clear that, as an example, the built-in if then else is meant to take a condition which is a boolean and two optional return values, and finally choose one of the two given return values based on the condition given. And of course, this is done for all the built-in function and values present in the Plutus core specification. Section 6 does give some examples that are useful to understand how to write Plutus code. And finally, we get to section 7, where is explained the untyped Plutus core. Now, here in section 7, it is important to have a look at figure 15, where it is introduced the grammar of untyped Plutus core from this moment on, also called UPLC. And here we introduce the term that, as we see here, is the main part of a program of, and a term can be either one of these specified here. So it can be a variable, in this case a free variable, meaning it is not bounded in any specific expression. And in section 2, it was specified that a variable is identified by a name, which is just a string of letters, numbers, and some allowed symbols. Then we can have constant as valid terms, lambdas, which do come with a variable which is meant to be a bounded variable to the term that follows. So whenever we encounter the same name in that term, and we know that in the term alone that name would be a free variable, when then we apply a lambda, we do recognize that name as a bounded variable and substitute what will be the right term into every occurrence of that variable into the term that is given in the lambda. Now, these are a lot of abstracted words, but we are just talking about an anonymous function that is present in most of programming languages, and Typescript and JavaScript do have such a feature too. Then we have a delay and a force, which are basically wrappers around a term value, and those two built-in functions aims to emulate the lazy evaluation of Haskell, even if untyped Plutus core is a strictly evaluated language. We do have also function application, as we also saw in the syntax definition in section 2. And then we have a built-in keyword specifying that the term that follows is a built-in applied to an optional term, of course, depending from the built-in that is being used. And then we also have ways to raise errors which do terminate the computation, failing the smart contract. And we see that the definition of a term is recursive, and that is why it is called an abstract syntax tree. Section 7.1 is about type erasure. Once again, we are not interested in this since we will only focus in on type Plutus core, and type checking will be done thanks to TypeScript and JavaScript features. So with section 7, the actual specification ends, but among the appendices, there is the Appendix D, which is very important since it gives us some important hints to understand how an abstract syntax tree of untyped Plutus core programs should be serialized in order to go on chain. And for this specific appendix, I do have prepared another markdown file, and here it is explained how flat serialization works for Plutus core programs. Now, the first 3 lines of Appendix D are very important since those give us a high-level idea of the flat algorithm to serialize data structures, and this link actually takes us to the flat specification that you can read yourself. And actually, the flat implementation is in Haskell, which is one of the main issues that may come with the implementation of serialization in languages different than Haskell. But fortunately for us, the Appendix D does give us a lot of hints to how to implement this serialization algorithm more in general than the flat algorithm itself. So here I do give some explanation of what is meant in the first 3 lines. You can read this. If you also have some Haskell knowledge, this will help understand better what is going on here. But the actual serialization starts with section D1, and in section D1 it is explained how variable length data is serialized in untyped Plutus core programs, and this is done by taking the, of course, variable length data and splitting that data in chunks of 7 bits, because we do need the first bit to understand when this variable length data does have its last byte. And here I do give an idea on how an utility function could be implemented in TypeScript to understand if a given byte is the last one. And by specification, when the first bit of the byte is at 0, this means that this is the last element, and when it is a 1, it means that there will follow for sure at least one other byte. So with this, we can encode variable length data. Then I pass to explain the section D3, since I think it's more important to understand how the term is serialized. And then we'll see section D2, which only explains constants. So in section D3, we do see that a term can be any of these values, and we do recognize which of these is our term by reading a 4-bit tag and expecting one of these values, which do correspond to that. And based on these 4 bits, then we know what to parse right next in our stream of bits, which is the serialized Plutus core program. Here I do have reported a quick table to explain this concept, and this can be read also as an high-level explanation of what will be the algorithm to serialize an abstract syntax tree of a Plutus core program constructed in Typescript. In section D3, it is also specified how built-in values that we first encountered in section 2 are identified, and we do use only 5 bits for built-in functions and values. And then going back to section D2, we see how constants are serialized. We do recognize a constant by the tag 4, and when we see a tag 4, we expect to parse another tag again of 4 bits to understand which constant are we going to see. And then we see how these constants are then serialized. We do have integers which do use the zigzag encoding. I do have included a quick explanation of zigzag, but a better one can be found just by searching for zigzag encoding. And here, as an example, we do find a very good explanation of how zigzag works, and it is basically an algorithm to uniquely identify signed integers as being an unsigned. Then we also have byte string, which is just a variable length piece of data. We do have also strings and chars, both encoded as variable length since they are using the UTF-8 encoding. The unit is only the tag, and we expect no more bits right after the unit, and a boolean is just, of course, the tag, and then one single other bit to tell us if it is a false or a true. And with this, we saw how it is possible to implement an untyped Plutus core abstract syntax tree and serialization in potentially any language. So now we'll just go back to our root and discuss a potential timeline, which is of course important. And here the timeline is more basic than the off-chain one, since the high-level idea is just to implement an untyped Plutus core abstract syntax tree, implement some utility function to build an abstract syntax tree, implement then the serialization, of course, of this tree, and based on these important features, then we'll use what we got until here to implement what will be the actual library with all the classes and the functions to help the developer to write his on-chain code in TypeScript.